All right, so I'll post two recordings for today. One that's about the kind of final exam stuff, which is the previous recording from the previous couple of minutes here. And then today, which is our technical content for today, which we're in a new unit, our last unit. So this is a unit on primarily on interacting particle systems, or IPS. And this comes out of the kind of, I kind of highlighted the title, this complex systems approaches to computation. So these largely started out as ways, as models for understanding complex phenomena in nature. What do I mean by complex? So we always talk about there's a difference between complex and complicated. So a traditional good old-fashioned watch, not like the things that are on my wrist right now, but a watch that has gears and all that, that's not complex, that's complicated. So a watch with gears and all those sorts of things, each individual component there's a lot of heterogeneous components and they fit together in funny ways, but there's nothing surprising about how a watch works. You just have to kind of know how each individual component, what it contributes to, and it has a particular role. So likewise, most engineered systems, modern engineered systems, are complicated. They're not complex. And so in an automobile, a mechanic knows what the function of every single part in that car is. There's a lot of parts, and they do a lot of things, and they go together, and the system needs, it's been finely tuned and engineered to work together, and it's a marvel in that. But if you can't start your car, you know exactly what the problems might be. It could be the starter motor, it could be battery. It's easy to sort of figure out what the source of these problems are. The function doesn't emerge. It's sort of prescribed ahead of time. We contrast that with complex systems, and in complex systems, every individual component interacts in a way that's understandable, but not understandable in terms of the overall system. So you can see that an ant bumps into another ant, and after she bumps into another ant, that ant changes her speed. And we might understand that. We could describe that, and it happens every time. Every time an ant bumps into another ant, the ant she bumps into gets a little faster. And then we zoom out and we look at the ant colony, and we see the ant colony is like balancing its checkbook or something like that. We don't have no idea how an ant bumping into another ant and it's getting faster relates to an ant colony doing something complicated like, effectively foraging throughout an environment. So the colony level phenotype of being able to find food sources and concentrate efforts on them emerges from interactions which don't have an obvious connection to that overall phenomenon that occurs there. So that's what we mean by complex. It's when we get a non-trivial function that emerges out of relatively understandable interactions, but so many of them that when combined with over time and space, then new sort of functional modules sort of self-organize. And with that in mind, there's actually a subset of interacting particle systems, or an area that people sometimes refer to as self-organizing particle systems, or SOPS. And I mention this because upstairs in the building next door, there is a ASU faculty member, Andrea Richa, who is a senior faculty here, professor in computer science, who does a lot of work in distributed computing, and her lab focuses a lot on self-organizing particle systems. And so she is interested from a computing perspective to sort of say, imagine if we had smart paint molecules that you could distribute. You went to the Golden Gate Bridge and you just dumped a bunch of them at the foot of the bridge, and they, like ants, started to move around. How do we guarantee, like a computer scientist would, that in finite time, the entire bridge, if there was enough paint, would be covered with these smart paint molecules? And then how do we guarantee that once it's covered with a thin layer, and that layer is maybe equal thickness all down the Golden Gate Bridge, if somebody were to scratch some of that off, that the excess paint molecules that are smart paint molecules that are at the edge would naturally fill in those gaps without any centralized control. So she builds, we don't have said paint molecules, but once we have them, we'll need algorithms for them. And being computer scientists, they'll need proof about the function of those algorithms. And so a lot of what her lab does is build these proofs of the distributed operation of such self-organizing, hypothetical self-organizing particle systems. And she works with people like at Georgia Tech, like Dan Goldman. He's a physicist who builds things that look like natural self-organized particle systems. Dana Randall, another Georgia Tech mathematician who studies Markov chains that describe self-organizing particle systems or interacting particle systems. And so, so that's kind of an example of where this stuff, is related to computing. But originally, these were used as kind of models for natural systems. So, for example, how do forest fires, for example, evolve? And even just general canopy dynamics. So, there's things like if you've ever gone out to the rainforest or really even temperate forest and you look up, you see these things called like canopy shyness. So you look up and if you actually see that there'll be like these trees, they'll have these like rivers of gaps in between them. So if I'm looking up at a bunch of at treetops, and so the sunlight is behind this view that I'm looking up, then you see that they actually form these gaps in between them. This is referred to as canopy shyness, or and so you say, well, how do they sort of decide who's going to go where, and why don't they ever overlap? And so you can come up with these tools for understanding in a distributed way how these resources naturally get cut up as things kind of interact with each other in space. So a lot of things here that are related to kind of interactions in space. And so this also goes down to things like developmental biology. And again, it's a lot of times explaining spatial patterns, like patterns on a zebra, or different spotting, spots, etc. On landscapes, as well as in different developmental forms. And so there's a bunch of distributed systems that are as small down as how a fruit fly develops to as big as how weeds grow on the side of a hill, and you see very similar patterns. And so the interacting particle systems community is sort of like trying to say, how do we build models that understand where these patterns come from? And I'll mention these people as we get a little bit farther, when folks like Stephen Wolfram got involved in this. So if you've ever used the tool Mathematica, his company built Mathematica, and so Wolfram is sort of a mathematician physicist who has gotten very interested in, and I'll mention it before, he's got a book called A New Kind of Science, which his kind of disciples refer to as NKS. And at this point, it's like, if we can build these fancy complex patterns in a computer simulation, maybe we can even learn from them without matching them to a natural system. And so people kind of started out saying, using these as models for existing natural systems you could find. Now, these models have become inspiration in themselves, where people just say, can we build things that produce exciting patterns over space and maybe learn something about complexity and emergence in general that maybe will have some transferability into thinking about natural systems. But sometimes I think this community doesn't really actually care if things end up connecting to the real world. They're sort of just even interested in the patterns themselves. And so so this is kind of the background, the context of what motivates a lot of people that work in these interacting particle systems. So I can give a kind of simple example of this that relates to something that we've talked about already. So, example from population dynamics. And so imagine if we've got a population of individuals that I'm just going to put each individual into a box here. And let's see, I'll put, it doesn't actually matter how many I put here. So just a bunch of individuals here. And those individuals, let's say they express, if we think of it in terms of genetic algorithms, maybe they have particular genotypes or particular alleles. And so I can say we've got allele A, allele B. How many did I put here? Let's say, just some combination of A, B, C, and D. The pattern here doesn't matter too much. And so let's assume that A through D have equal fitness. But the population size is maintained. And so then the question would be, over time, Gesundheit, what would be the distribution of individuals that we would get after a long amount of time? And can we describe this equilibrium distribution? Now this, I hope that you see here, is basically describing drift back from when we talked about GAs. So we kind of know that in these population systems and evolutionary systems, if there's no differential fitness, then you're going to get random outcomes. Or even if there's very low differential fitness, but here I'm considering no differential fitness, just due to random chance, you can get fixation on either A, B, C, or D. And it's kind of like whoever had the head start is most likely to be the one who's going to end up taking over. And so, but we like to sort of have a more mathematical handle on whether this happens, what's the distribution of maybe what's the distribution across A, B, C, and D of which one's going to take over, and are there special cases where this maybe wouldn't happen, even though our kind of toy model here suggests that maybe it'll always happen. And so a model from the IPS group or literature that was meant to sort of model this was the so-called voter model. And so what is a voter model? So this is an interacting particle system. So in a voter model, we can think of each site as a voter with preference for candidate A through D. But then these voters can interact with each other. And so at the next instant of time, then we're going to say that each individual A, or each, sorry, not each individual A, each individual at each individual site is going to, with some probability, it's called probability gamma, pick a random opinion from some neighborhood around that individual. So at each step, each site picks with probability gamma a random other individual to copy or imitate from a neighborhood. And what I mean by from a neighborhood is we can define that, let's say for this individual, the neighborhood are the three that are next to it. So this individual is the focal and these are it's in its neighborhood. Maybe for this individual, the neighborhood is, for some reason these, like, so there's some topological reason that these are the connected neighborhoods. Or it could just be simple and it could always be the two individuals to your left and right with special cases at the end. And we might consider these actually having rotating boundaries. So if you're the focal individual here, your neighborhood is the two to your right as well as the two that are over here. So that could be your neighborhood. So there's some neighborhood pattern, and we could actually write that neighborhood pattern out as maybe a network, who's connected to who, where we could say A, or position 1 is connected to position 2 and 3, as well as whatever these positions are, 14 and 15. And the point, all we're going to say here is that neighborhoods have the topological property of being irreducible. And I'll describe what that means in a second. Are irreducible by assumption. And what that means is that they're always, from any one individual, you can always get to another individual through a chain of steps. And so if we were to connect all these neighborhoods together into a network, there's always a path from one individual to another. So I'll just say a path exists from one individual to any other. Well, I should say from any individual to any other. So it doesn't have to be in that individual's neighborhood, but that individual is connected to another individual who's connected to another individual, so that in principle, information could be shared from one individual to all other individuals on this network. And so that's the basic voter model. And so we're viewing this as, you can think of this as a model of pure genetic drift. And so then the question would be, what happens? What is the outcome? And so we view this as an interacting particle system because each one of these is a particle and it makes its choices about its next behavior based on its interactions or its observations of other particles that are around it. So it's a simple thing. So an interacting particle system, nothing too complicated. It just basically means that we've got a bunch of individuals that exist. You can often think of them as embodied in some sort of space. And because they exist in space near other individuals, they have an opportunity to interact with other individuals, and those interactions trigger changes. And those changes might be the individual changing their identity, an individual maybe producing another individual, an individual dying, and so on and so forth. And so the voter model is kind of a simple example of this. So if we want to consider what happens to this, we might, and then, so what is the outcome? And then also I'm gonna add, just as sort of a hint, does it depend on dimension? What do I mean by that? What I mean is, like, I have lined up these individuals on a line right here. Now, I could have also lined the individuals up in a plane so that I have individual 1, 2, 3, 4, 5, 6, and so on. So, in this plane here. Now, I could have also lined up individuals in 3D. So I'd have like an individual here, an individual, down this axis, individuals down this axis, up this axis, and everywhere in between. And so we could define, one-dimensional neighborhoods, two-dimensional neighborhoods, three-dimensional neighborhoods. And a question might be, does it matter? Will I get the same outcomes of this, over time? Or in other words, the big thing I'm wondering about is consensus. So I know that in this drift process up here that I'm kind of inspired this voter model, I know that in pure genetic drift, then you get fixation on one strategy. And so then the mathematical question is do I always get fixation in every kind of topological setting? Is it possible for me to have an irreducible neighborhood and not get fixation because of the dimension of how the neighborhoods is laid out? And that seems kind of funny, but that's where, the fact that I'm asking the question suggests that dimensionality is going to matter. So, so how do we analyze this process? Well, and let me make sure, I might have saw a question pop up a little earlier. So there was a question back about the report. Just in case it wasn't obvious earlier, the report and the presentation are due at the same time. They're both due Wednesday night. And that way you can peer review. All the peer reviews will happen sort of at the same time, and everybody will be able to peer review your report and the presentation. So you don't have to wait on one or whatever. So yeah, they're all due at the same time. Okay, so if I want to analyze what goes on here, if I think about this simple drift model, so like I said, there's a width probability here. So this, I should be able to use stochastic modeling here, right? I should be able to think of this as like a Markov chain, and I could sort of say like that in this case here, you could imagine that there's this kind of Markov chain. So imagine kind of from a one Markov chain interpretation. Then I might have a state, which is going to be the all A state. And then I have an all B state, and an all C state, and an all D state. And then I've got a bunch of other mixtures in between. And in principle, if I know the mixture and I know the neighborhoods, then I could, in theory, calculate a probability of transitioning from one mixture to another. And in that, those would bounce around. But eventually, once you got to the all B state, or the all A state, or the all D state, or the all C state, then there's no outgoing arrows. And so things would stop. So these here are absorbing, so the corners are absorbing states. So consequently, this Markov chain is not, and I'll just use this fancy term, ergodic. And I don't want to go into this because it's not a class on Markov chains, but what I will say about this is that ergodic Markov chains are super easy to analyze. You give them a high schooler and it's fine. But when they're non-ergodic, it's just complicated because you don't have as much regularity. You can just, bad luck can cause you to hit an absorbing state. And once you're in that absorbing state, you can't get out of it. So when you have a non-absorbing Markov chain like this, one that's not ergodic, then you might start asking questions like, what's the probability that I land in the all A state? Well, that's going to have to depend on what state you started in. So it just gets, the questions here get ugly. and there's less mathematical tools that are available to work with these non-ergodic or these reducible, that's another way to view these things, Markov chains. So basically what I'm saying here, a lot of times we talk about ergodic Markov chains, we also refer to with the term irreducible. It's kind of a similar, these two terms are related here. What we're basically saying is so much goes on in these states, but because these states are absorbing, they kind of are where all the focus are. So like all the dynamics happen in these states don't really matter, because if you accidentally hit one of these states, you don't ever get back into here. So that's kind of the fundamental tension, is that these are sort of transient states. They're like, and we might be able to describe what happens, but we really need to know exactly where you start in order to figure out what path you're going to take through all these states. And in the end, you're going to end up in one of these states anyway. So, so that's because they're all sort of transient. We review these chains as being reducible, which basically means we don't care about these things. We can get rid of them. And if you just replace the Markov chain with the absorbing states, then that sort of captures all of the generalizable properties of the Markov chain. So if you have an irreducible Markov chain, then that means that you don't have these absorbing states, and that you can always get back to any state regardless of where you started. And that makes it much easier to analyze, because every state becomes important. Whereas here, you've got a bunch of states which are kind of quasi-important, but aren't really that important. And so these are just difficult problems to deal with. And so the voter model seems like it would be a difficult thing to analyze formally. But there's a clever thing that we can do with Markov chains. We can time reverse them. And this actually becomes really important when we think about epidemics, contact tracing. If we all get sick, then a natural question is to say, who was patient zero? Well, how do we figure out who patient zero was? We contact trace. We say, well, who did you bump into, when you got sick, and whatever, whatever. And you eventually see that person A got sick from person B, and whatever, and all that sort of things. And eventually you lead back and you see that, oh, person Z caused it. They were the first one to get sick. So if we want to know what sickness we all have, it's person Z's sickness. And that's what we want to do with this. So if we want to sort of see that, like, well, if everybody gets opinion A, if everybody decides to vote for candidate A, then what we can kind of do is kind of contact trace and say, well, who convinced you to vote for person A? And so on and so forth. And eventually you find the one person who initially was voting for A without any of the trend setter. And if you can find that one person, then you kind of know that was the process there. That's what led us to this thing. And describing this contact tracing process in reversal time generates a Markov chain we can analyze. And so this is what we refer to as the dual process. And this is just time reversed. And so imagine if I've got, this is on this axis here. All right, so I'm going to plot reversed time on this axis. So time 0 is going to be at this point way over here. On the y-axis, I am going to I'm going to give each individual so if I go back to my simple example of this linear case here, I'm going to like name these individuals. Like this will be individual 1, 2, 3, all the way to whatever individual this is. And so I am going to, so what this time reverse trajectory is going to be is going to trace the opinion of an individual back through the individuals it copied from. So if I've got, so this time here, this is going to be T. This will be the end of process or end of observation period. And so this will be one step before that, one step before that. How far do I want to go? this goes on until eventually, maybe I'll get 3, 4, 5. Okay, and then what do I plot on the y-axis here? So if I have, I'm going to say this is individual 0. Let me see if I can get 6 in here. 1, 2, 3. And then I am going to also plot 0 again. And I'm going to say these are 6 individuals on a torus. So that basically means we've got a boundary wrapping. So we got 6 individuals on the donut, so that individual 0 is next to 1 as well as individual 6. And that's the reason I've kind of drawn them this way here. And what I can sort of keep track of is what each individual's opinion, sort of its origin. So I can say like individual 6 maintained her opinion for these 2 time steps. But you can say, where did she get her opinion? Well, she got her opinion from individual 5 at time step t minus 3. So that's what this, again, this is kind of a contact tracing thing here, is that individual 6 didn't make any changes here, but she originally had a different opinion at t minus 3. And then she sort of transferred her opinion to whatever individual 5's opinion was. And so we can say that, so she took individual 5's opinion. So at this point, well, I'll draw a couple of these and we'll see what happens here. But what I'm going to get to is it's like individual 6's history, and by individual 6's remember, history is kind of moving in this direction because we're moving in time reversal. It actually doesn't matter. Once I know that individual 6 got her opinion from individual 5, all I have to do is trace individual 5 from that point on back, because I really just want to know, where did individual 5 get her opinion? And I can do this for other individuals here. So I can say individual 4 had his opinion for 1 time step, but where did he get that opinion? He got that opinion from individual 2 at the previous time step. And individual 1 had his opinion for 2 time steps. Where did he get that opinion? He got it from individual 4, interestingly enough, at the same time step that individual 4 grabbed his opinion from a different individual. Now, those, they might have both gotten their opinion from individual 3 here. So the idea here is that this individual 3, its opinion spread to individual 4 as well as individual 2. Now, individual 2, it ends up giving its opinion to individual 4. Individual 4 gave its opinion to individual 1, but both of these came from this one individual here. So at this point, we kind of can keep track of the final opinion that 4 and 1 have by keeping track of where the opinion came from, just by seeing what individual 3 has in its history. Because remember, history is going in this backward period here. So what I'm trying to say here, and I guess I can imagine you continue this process on back, every time 2 of these lines connect together, they become 1, and they coalesce into 1 line that we follow, only that line from that point on forward. So at this point, everybody's got individuality. We can draw lines back from every individual, but those lines eventually will collide with other lines, and then those lines will end up being the only thing you trace back until you may only have 1 line in the past. And so if I were to keep doing this process, then I might end up with individual 3 we see its opinion, maybe individual one, or maybe some other individual that I haven't talked about, two. These two end up connecting together. And then from this point, maybe I'll use five because I haven't done with anything with five before. It's just this kind of one line that maybe hops around a little bit. And so on, but so that you start out with a bunch of individuality and then you end up just sort of having, this is kind of a patient zero. And so it's sort of a contact tracing of opinion sources. And this is what we refer to as a coalescing Markov chain. And what I mean by that is, although the actual physical process that drove this whole thing was going from time zero into the future, it generates a trace whose statistical properties are consistent with a Markov chain that somehow started in the future and then progressed into the past. So mathematically speaking, we can model probabilistically the evolution of these lines as they move and coalesce with each other as a Markov chain moving in the reverse, instead of worrying about the actual physical Markov chain, which is moving forward. And the statistics are identical. So it doesn't matter to us whether we're moving in forward time or reverse time. We can choose the Markov process that is more convenient to analyze. And it turns out this dual process is, I called it a coalescing Markov chain. It's actually, more generally, this is called a coalescing random walk. But it just so happens that this random walk also is a Markov chain. And what's interesting about this Markov chain is that it is ergodic. It actually, and this is ergodic, which basically means that if we focus on the chain that's going in the past, this chain can reach every state. So if we were to ask, like, now this state, the state of this process here, because it's coalescing, it starts out as hairy, as a bunch of different processes here, but each individual process has the possibility, each state, of reaching any other state. So regardless of if you were, individual 6 or individual 1, the history has a possibility of crossing into the history of anyone else. And that's what makes it irreducible. That's what makes it ergodic. And ergodic Markov chains have a bunch of useful properties we can immediately make use of. And that was what was realized when people started analyzing these. And so, so there's a well-known result in these ergodic Markov chains referred to as Kolya's recurrence theorem. And the way this is just a well-known result in, I'll say, ergodic Markov chains. And what it says is that a random walk will visit any point, including a starting point, with probability 1, so long as the dimension of the random walk is 1 or 2. So we're saying here that I'll say that again, is that a random walk will visit any point including the starting point, including its original starting point, eventually with probability 1, so long as, or I'll say in the case where the dimension is 1 or 2. So in a 1 or 2 dimensional Markov chain, you're guaranteed that as you're moving around the chain, you will hit every point with probability 1, including the original point that you started at. So this is what Roombas work off of. So the idea, roughly speaking, is that when you would put a robot on a floor and you have it bounce randomly off the walls, then you have some, I'm drawing a little bit of liberties here, but it's strongly a related result. But you have the result that that robot will hit eventually every point on the floor. And if you need it to exit the room, it'll eventually find the exit to the room and leave the room. It might leave the room before it's hit every point on the floor. So we're not actually putting any temporal logic specifications on here, but we're guaranteed that it's not going to get stuck in the room forever. It might get stuck in the room, like its battery might not last as long or whatever, and all that sort of thing. But as long as it's long enough battery, it will find its way out of that room. As long as it's a one-dimensional room, a line, or a two-dimensional room. And that's kind of what all we're sort of saying here. Now, the interesting thing happens is that for dimension 3 or higher, this is not the case. So for dimension 3 or higher, then there is the probability is less than 1, strictly less than 1, that the random walk will visit every point. And then so if I'm thinking of this in terms of coalescing random walks, then this means that every walk will coalesce into one. And then here, you can have multiple walks fail to coalesce. So this, to me, is a really kind of cool result, because what we're saying here is that you can actually have, so this implies you can have a failure to reach consensus in the voter model when the dimension is 3 or higher. So that fixation that we thought was just a natural property of evolutionary systems, it turns out it's actually related to the structure of the dimensionality of how neighborhoods are built. So there's a topological feature here that can allow certain traits to escape being replaced by other traits. So if you live on a line or in a plane, then this coalescing property here basically means everybody's going to get sick. So there's no way for an opinion to not eventually reach everyone. There's always going to be one opinion that will dominate. Here, you'll always get consensus. So this is saying always consensus in voter model. But down here, it's this interesting result that if you're moving around a three-dimensional space, then it's possible for two opinions to constantly be missing each other in the night, just sort of two ships passing in the night. And so it's possible for a group of people to sort of be, interested in one opinion, and then before that opinion has the chance to convert people in another group, enough people in this group get switched over to that opinion and vice versa. And you can get this kind of standoff between these two opinions that are constantly spiraling around each other, and the walk's never actually coalescing. So this failure to coalesce is a failure to reach consensus. And this comes from modeling these interacting particle systems in this kind of more formal way that allows us to have this kind of interesting result. Now, in most of our genetic algorithms and things like that, if you really think about the topologies of how the selection processes are going on, where they aren't three-dimensional topologies, and that's the reason why fixation is sort of so much of a problem. But you could engineer systems that exchange opinions about the temperature of the room or whatever, if it's a distributed sensing problem or whatever. And if their connection, their network topologies can't be flattened into a plane, then that's going to imply that you can actually get a failure to reach consensus, even though you're using an algorithm that in principle you might conceptually think is always going to eventually reach consensus. So, and by that I mean, like, if I put a bunch of sensors in this room and they all try to estimate temperature, and I can say, well, how do I get a good estimate of the temperature in the room? Well, one kind of dumb way to do that would be to say two sensors that disagree, one just agrees to take the reading of the other sensor. And so I could say if sensors are constantly asking their network, what's your temperature reading, and then randomly deciding to take one of the other temperature readings instead of their own, if they have a network topology that's planar or less, then it's guaranteed that they'll all eventually agree on a temperature estimate, as long as the temperature doesn't keep changing. It's like a snapshot in time. But if they have a connection topology that cannot be flattened into a plane, then it's possible that they'll never actually reach consensus, even though they're using the exact same process. So that's kind of a cool analysis there. And I think it's kind of a neat use of this dual model, where we actually think of contact tracing as a time-reversed random walk. And then we analyze the random walk moving backwards in time instead of analyzing the forward process. So, and this is, you can use this trick in other similar systems as well. All right, so that's kind of, my introduction to the voter model. Is there any questions about that? So the voter model is kind of a generic interacting particle system. Where I'm going to go with this is cellular automata, which are more well-known interacting particle systems that people like Wolfram and all that have gotten very excited about, and are, I guess, much more feasible for computational models as opposed to these mathematical models. So that's where we're going. But I just wanted to give you an idea of sort of one of your kind of classic interacting particle systems, the voter model. And if you were to Google there's all sorts of embellishments in the voter model that are trying to understand what happens when you just swap ideas, swap diseases, and so on, and you constrain how those swaps happen. When do you get consensus and when don't you? All right, so any questions, comments? Everything aligned still about the report? Okay. All right, so for the last couple of minutes here, so like I said, how many people have heard of cellular automata or seen cellular automata CAs? Okay, so where we're going then in the last two lectures is then, a cellular automata are a special form of IPS. And these are particularly well suited for computational analysis. And if you haven't seen these before, you've probably, it wouldn't surprise me that you maybe have, but maybe just didn't recognize them as being called this. But these are the things where, like, if I've got a grid of cells, and I put a 0 or a 1 in each cell. And I set up a set of rules. Again, it's an interacting particle system. And those rules are described maybe deterministically. So I could even have nice deterministic rules. And those deterministic rules might be that next cell is some function of the current cell and neighbor 1 and neighbor 2. And so you might say that if your cell value was a 1 and your neighbors were 0 and 0, then that might mean that in the next iteration, your value would be a 0. So, this deterministic rule might be an even detector. So even detector. So this would be 1 if even number ones, odd, or 0 otherwise. And so once you have one of these deterministic rules, you could apply it to this whole row, and that will generate a new pattern. Then you can apply that again, and you get a new pattern, and so on. And you get this thing that's sort of related to something in mathematics we refer to as an iterated map, where you're kind of applying a function to itself over and over again. So you have some initial condition, and then you sort of ask what happens as you take this process to kind of infinity. So deterministic rules, deterministic function. So this is how we're getting kind of a more specialized case of interacting particle systems. And what we'll see is that even with simple deterministic rules, you can get some pretty interesting patterns. And we'll actually see that certain sets of these rules are what we refer to as Turing complete. So you can actually program any program you want into the initial conditions, and this will actually calculate it if you choose the rule correctly. So that's where we'll go next time. Don't want to keep you any longer. So if you have any questions, feel free to come up after. Otherwise, we'll see you, I'm sorry, not Thursday, Tuesday. So have a good weekend. Muddiest point, I think, is the only thing you have to worry about. And then take a look at that practice exam, make sure it's working. Are there any other questions online? In that case, I will go ahead and end the recording.